A groundbreaking AI just launched, performing like much larger models, but with incredible efficiency for real-world tasks. This breakthrough sets a new standard, making powerful AI more accessible and capable of solving complex real-world problems. Let's get into it. Let's start with a featured paper, Mach-Mind-4-Flash Technical Report, by Foundation Model Team. This work represents a landmark result in model efficiency, delivering the capabilities of a much larger model class through post-training alone and setting a new standard for the field. Here's a full breakdown.
Starting with our first contribution, let's trace the OPD path from the central routing decision. This path engages the teacher GPU pool to generate expert outputs, which are then used to compute the OPD distillation loss for training. Next, the RL path handles our policy optimization method. After calculating rewards and advantages, this information feeds into the RL policy gradient loss, which specifically uses our GSPO policy loss to improve token efficiency. Mach-Mind-4-Flash demonstrates strong performance in instruction following and safety benchmarks, notably achieving 98.20 on Content Safety Bench. However, it is often outperformed by other models in reasoning and knowledge, tool use, and OpenClaw tasks.
Up next, our second paper out of 10, a safety-oriented hypothetico-deductive framework for AI-assisted differential diagnosis by Fan Ma and Kent McCann from Yale University. This paper provides a critical, safety-oriented framework for applying LLMs to high-stakes domains, moving beyond simple prediction to a robust, verifiable reasoning process. Let's break down its key contributions.
Let's start by looking at the overall structure of our proposed ArXiv framework, which is laid out here. It's a multi-stage pipeline that begins with hypothesis generation and flows through several verification steps to produce clinician-facing decision support. Feeding into the first stage, we have several coordinated LLM components, each with a specific role. For instance, the multi-specialist agents collaborate to generate initial differential diagnoses from the patient case. Next, the framework uses structured intermediate outputs to guide the process and ensure information flows clearly. A key example is this diagnosis list, which is generated by the first stage and serves as a concrete input for the next. To ground the system's reasoning and medical evidence, we integrate evidence retrieval interfaces. Here, the searching agent queries external knowledge bases like PubMed to verify the diagnoses on our list. Finally, a critical safety feature is the inclusion of verification gates to screen for dangerous conditions. The warning agent acts as one such gate, identifying and flagging potential should not missing diagnoses to ensure they are properly considered. ArXiv consistently achieves the highest top 3 accuracy, outperforming all other general, medical, reasoning, and agentic LLM systems shown. Furthermore, ArXiv substantially improves top 1, top 2, and top 3 accuracy for various standalone LLMs, with gains ranging from approximately 4% to nearly 20%.
Up next, our third paper out of 10, Toolmaking and Self-Evolving LLM Agents in Low-Latency Systems by Kali Kajampa and Shervin Malmasi from Amazon. This paper presents a paradigm-shifting approach for production LLM agents, moving from inefficient, repeated inference time coding to a robust, precompiled toolmaking pipeline that will likely become a standard industry practice. Let's break down its key contributions.
First, let's look at the offline toolmaking process at the top of the diagram. This entire pipeline takes a specification from an SOP node, processes it through several agentic steps, and ultimately compiles it into a validated, deployable tool. Feeding into this, the core of the process is the toolmaker LLM, which generates candidate code. This code is then passed to a test stage, and if it fails, a reflector LLM analyzes the failure to create a repair plan for the toolmaker in an iterative loop. Next, we see the result at runtime in the after panel. Instead of the main agent needing to spin up multiple subagents, it now makes a direct, efficient call to the precompiled tool to perform the required action. The GLM 4.7 model, when enhanced with both +D and +R, achieves the highest performance of 94.5. This significantly outperforms its SOP baseline and other models like Qwen 3235B and is slightly better than GLM 5.
Up next, our fourth paper out of 10, Token Flow Firewall, Semantic Runtime Auditing for Persistent AI Agents by Puji Wang and Sweki Chung from Institute of Computing Technology, Chinese Academy of Sciences. The paper introduces a novel and necessary security paradigm for persistent AI agents, moving beyond simple I/O filtering to a semantic firewall that tracks unsafe content as it flows through the agent's internal state and tool interactions. Let's break down its key contributions.
First, let's trace the fundamental path we're securing. Data originates from various sources, like user input or web APIs, and is directed towards a system. This entire security process is orchestrated by our framework, Token Wall, which you can see enclosing the three main stages. It acts as a semantic firewall, intercepting and analyzing these data flows before they can cause harm. Feeding into the core of the system, the local small auditor performs a boundary-aware semantic judgment on the token flow. This allows it to understand the context and intent behind the data transfer. Next, notice the layered inspection approach, which ensures efficiency. After an initial pre-check, ambiguous or high-risk cases are deferred by the local small auditor and escalated to the large arbiter for a more powerful, in-depth analysis. Token Wall achieves the lowest scores in context, authority, and overall metrics, and ties for the lowest in capability, outperforming methods like Open Guardrails and Secure Claw in these areas. It also provides significantly lower latency compared to most claw-based methods, although its recall rate and hit rate are not the highest among all competitors.
Up next, our fifth paper out of 10, Better Harnesses, Smaller Models, Building 90% Cheaper Agents via Automated Harness Adaptation by Chenyang Yang and Christian Kastner from Carnegie Mellon University. This paper introduces a clever and highly practical method to drastically cut agent inference costs, directly addressing the single biggest barrier to their widespread adoption. Let's break down its key contributions.
At the top, we see the core problem, a gap between a model's capability and the task demands, which leads to failure modes. Our approach is to bridge the gap with harness adaptation, using a meta agent to automatically customize the setup for a small model. Feeding into this, the system first identifies specific failure modes on the left, such as issues with tool use or following instructions. This framework then systematically links these observed problems to potential solutions. Next, a harness optimizer automatically selects from a menu of adaptation strategies on the right to fix those failures. These strategies range from adding context and creating tools to orchestrating multiple agents. The optimized harness method substantially improves the average performance of small language models. For example, boosting Gemma 4-26b, A4B's average score from 31.4 to 80.2. This optimization leads to significant gains across most individual metrics for all small models, often transforming their performance from poor to good or best.
Up next, our sixth paper out of 10, When LLMs Agree, Are They Right? Auditing Self-Consistency and Cross-Model Agreement as Confidence Signals by Kaihua Ding from University of Pennsylvania. This paper presents a critical and surprising finding that debunks the widely held assumption that agreement among LLMs indicates correctness, revealing a systemic failure mode with profound implications for evaluation and reliability. Let's break down its key contributions.
Here we're looking at the results from our large-scale study, which generated these risk coverage plots for different confidence signals. The charts show performance for the GPT 4.1 mini model on two different datasets, GPQA Diamond on the left and AIME on the right. Feeding into this, the y-axis shows selective risk, which is calculated based on our majority correctness labeling. This essentially uses the consensus answer as a ground truth to measure how often a given confidence signal is wrong. Next, to analyze the relationship between agreement and correctness, we used a robust hierarchical bootstrap method. This statistical approach is what allows us to generate these risk coverage curves and be confident in the trends they show. While this particular view shows the results for GPT 4.1 mini, our analysis didn't stop there. We also conducted a cross-family comparison with Claude models to see how these agreement patterns hold up across different providers. Finally, to help the research community build on this work, we're making our data publicly available. All the de-identified per-run data used to generate these plots has been released for others to use and verify. The GPT 4.1 CE model achieves a high average consistency of 0.89 on the GPQA benchmark, outperforming other GPT 4.1 variants in this specific metric. However, for the AIME benchmark and correlation metrics, other GPT 4.1 mini configurations, such as the COT-B variant, often show stronger performance.
Up next, our seventh paper out of 10, Multi-Agent Autoformalization of Tensor Network Theory by Sirui Liu and J. Ignacio Cirac from Max Planck Institute for Quantum Optic. This paper presents a landmark demonstration of AI-driven scientific discovery, successfully autoformalizing a key theorem in theoretical physics, and even discovering novel proof routes. Let's break down its key contributions.
First, let's look at the core of our system, which is a team of specialized AI agents, like the reviewer and lean search agents shown here. These agents work together to autonomously formalize complex mathematical statements from theoretical physics. Feeding into this, the agents orchestrate a complete formalization workflow, starting from the primary literature. They transcribe and unify notation to create a blueprint, which is then formalized and proven to produce the final lean for machine-check theorem. Next, to coordinate their actions, the agents use a structured mathematical blueprint. This central document, written in LaTeX, contains the unified statement and notation, guiding the agents and ensuring the final formalization is coherent. To ensure correctness, the workflow integrates periodic human review, represented here by the human supervisor who sets and audits the intent. This crucial step helps enforce the high-level mathematical goals throughout the process. Finally, the result of this entire process is the Lean-4 MATLib machine-checked theorem, which is a fully verified formalization with no placeholders. This work produced extensive new tensor network and quantum information libraries that were not previously available in MATLib. The multi-agent autoformalization method, represented by agents like Lean and Lean Orchestrator, consumes substantial resources, with Lean processing 12.9 billion tokens and Lean Orchestrator incurring the highest spend at $8,702. This visualization details the internal resource allocation across different agents and large language models, but does not present a direct performance comparison against prior work or baselines.
Up next, our 8th paper out of 10. Video generation models are general-purpose vision learners by Letian Wang and Christian Smincescu from Google DeepMind. This paper advances a bold, field-shaping thesis for computer vision's GPT-3 moment and, if its claims are validated, introduces a new pre-training paradigm and foundation model that will change how the field builds generalist vision systems. Let's break down its key contributions.
Our approach starts with an input video, which is first converted into a sequence of video tokens by a V encoder. These tokens are then fed into the core of our model, a powerful pre-trained diffusion transformer, or DIT, which provides foundational knowledge about video. To get our final predictions, the system operates in a direct, feed-forward manner, avoiding the slow, iterative process of typical diffusion models. For dense tasks like segmentation, the output tokens are passed through a V decoder to reconstruct the final video. Finally, the entire process is steered by a simple text prompt, which specifies the desired vision task. This prompt is encoded into text tokens that condition the DIT, allowing it to flexibly switch between tasks like depth estimation, pose detection, and more. The proposed methods demonstrate strong performance across various tasks, significantly outperforming prior work in normals and expression-referring segmentation. For instance, our Specialist L achieves 76.4 GNF on Ref Davis and 70.0 GNF on Mevis, which are substantially higher than other methods.
Up next, our 9th paper out of 10. Can the cloud drive? Infrastructure feasibility of offloading autonomous driving across 5G and 6G by Priya Parsa and Seongjin Choi. This is a landmark systems analysis that rigorously evaluates the feasibility of a paradigm-shifting architecture for autonomous driving, directly addressing the immense real-world problem of hardware cost. Let's break down its key contributions.
Here's the overall analytical framework we developed to see if the cloud can really drive a car. It's a multi-stage process that takes us from checking basic network capacity all the way to a final economic decision. Feeding into the framework, we start with the communication requirements model, which is our first feasibility gate. This checks if the network can even handle the uplink demand from a given number of active vehicles in a cell. Next, we analyze the cloud-side latency, which is critical for control. Our latency budget decomposition breaks down the total 300 millisecond time limit, separating the predictable, deterministic delays from the variable, stochastic ones. Finally, if the system is technically feasible, we perform a cost crossover analysis. This is where we figure out the exact conditions under which offloading to the cloud becomes cheaper than using powerful onboard hardware. The query-level offloading method, S3, significantly reduces the required communication technology, predominantly operating within 5G capabilities across a wide range of utilization and AV penetration. This is a marked improvement over raw sensor offloading, S1, which often demands 6G or becomes infeasible, and feature-level offloading, S2, which frequently requires 6G or 5G advanced.
Up next, our 10th paper out of 10, a sovereign, open-source foundation model for German and English by Benedikt Droste and Lukas Helf from LMind. This is a landmark open-source release, providing a powerful foundation model with a novel, highly efficient hybrid architecture that will likely see wide adoption and shape future model design. Let's break down its key contributions.
Our work is built on a novel hybrid architecture, which we train through the 3 phases laid out here. The process kicks off with Phase 1, a diverse pre-training stage using a massive data mix. A key feature of this architecture is its efficiency, which allows us to process huge amounts of data with only a fraction of parameters active at once. This is crucial for handling the 23 trillion effective tokens in Phase 1 and the 6 trillion in Phase 2. Finally, to ensure strong bilingual performance, we employ a sovereign pre-training strategy that upweights German data. Looking at Phase 1, you can see we dedicate 7.2% of our initial pre-training mixed specifically to German. SUFI S30B. A3B consistently demonstrates superior performance across a wide range of benchmarks, frequently achieving the highest scores. It particularly excels in code, mathematics, and German language proficiency, often outperforming other models by a significant margin on tasks like Human Eval and GSM-8K.
Those were the top papers. Now, let's zoom out. ArXiv received 929 new computer science papers across 57 subfields over this window. Here are the trending areas shaping the field. Looking at the bigger picture, today's AI landscape is a fascinating blend of deep theoretical work, like optimal consensus, and highly practical applications, especially in generative visuals and LLMs. Let's take a quick look at each.
Trend 1 of 10, ML prediction under data constraints. Machine learning models predict outcomes despite limitations like scarce, incomplete, or complex data. This cluster covers 94 papers. Representative work includes expressivity and statistical trade-offs in diffusion policy learning, PathBoost, a Python package for interpretable graph-level prediction using path-based gradient boosting, and physics-informed machine learning under small data constraints. Lessons from abrasive waterjet milling. Trend 2 of 10. Generative AI for visual creation. Advancing generative AI models, datasets, and techniques for creating, refining, and understanding diverse visual content across various domains. This cluster covers 79 papers. Representative work includes Nigeria Machinery, a low-resource industrial dataset with a domain-grounded reasoning layer, Lightcrafter, PBR-conditioned video diffusion refinement for controllable and consistent relighting, and Dream Character 1, from 3D generative foundation models to product-ready character generation. Trend 3 of 10. Optimal consensus in multi-agent systems. Focuses on methods for multiple agents to reach optimal agreement or shared understanding efficiently. This cluster covers 68 papers. Representative work includes from Bayes' rule to Bayes' rules, optimal information processing and axiomatic foundations beyond probability, provably optimal learning algorithms for assistance games, and Declips, distributed consensus-based localization with passive listening on shared state exchange. Trend 4 of 10. AI for software reliability and security. AI techniques enhance software reliability, security, performance, and correctness across various development and operational stages. This cluster covers 98 papers. Representative work includes KSCFA, control flow attestation via symbolic replay against control flow bending attacks, Perfopt bench, evaluating coding agents on software performance optimization, and who broke the system, failure localization in LLM-based multi-agent systems. Trend 5 of 10, boosting AI performance with hardware. Innovations in hardware design, optimization, and architecture enhance AI model efficiency, speed, and reliability across various applications. This cluster covers 114 papers. Representative work includes LIST, Lipschitz scaling training for robust and calibrated neural networks, toward a unified, GPU-aware OpenSCMEM specification, and CRIMP, compact and reliable DNN inference on in-memory processing via crossbar-aligned compression and non-ideality adaptation. Trend 6 of 10, LLM Applications and Vulnerabilities. This trend explores diverse applications of large language models and investigates their inherent weaknesses and potential exploits. This cluster covers 147 papers. Representative work includes forensic schema for psychological manipulation and cyber fraud, LLM-driven victim reports analysis, from execution to education, a Bloom-aligned framework for measuring educational control in LLMs, and a transdiagnostic space of disorder like phenotypes in reinforcement learning agents. Trend 7 of 10, Advanced Mathematical Modeling Techniques. This trend explores sophisticated mathematical frameworks and computational methods for analyzing, simulating, and solving complex problems across diverse domains. This cluster covers 75 papers. Representative work includes off-site enforcement of natural conditions on smooth boundaries for finite elements upon fitted straight-edge triangular meshes, tree-based solution representations for quadratic bilinear systems and their consequences in model order reduction, and thermodynamic structure and composition in nonlinear convection diffusion. Trend 8 of 10, Robotics for Rehabilitation and Navigation. Developing robotic systems and AI techniques for human rehabilitation, including assistive devices and movement analysis, and for autonomous navigation in diverse environments. This cluster covers 77 papers. Representative work includes towards soft robotic exogloves for musculoskeletal manipulation to reduce pain and spasticity, evaluating the effect of frame rate in sequence-based classification of autism-related self-stimulatory hand idiosyncrasies, and time-to-collision-based dynamic obstacle avoidance using pre-trained vision models for robots in unstructured environments. Trend 9 of 10, Theoretical Foundations of Data Analysis. This trend explores the mathematical, statistical, and algorithmic underpinnings crucial for robust and efficient data analysis methodologies. This cluster covers 97 papers. Representative work includes smoothing exponents and decoupling in semi-finite von Neumann algebras, size independence of consistency index for pairwise comparison matrices in analytic hierarchy process, and domination and coverage problems under vulnerability constraints. Trend 10 of 10, Visual AI, from Pixels to Ethics. This trend explores visual AI, spanning foundational pixel-level processing and reconstruction to ensuring robustness, fairness, and ethical deployment of visual systems. This cluster covers 80 papers. Representative work includes named curves, learned image enhancement via color naming, 3D reconstruction of deciduous trees using low-cost UAV, and crane-based photogrammetry for monitoring shoot elongation across entire canopies, and towards robust semantic video transmission over block erasure channels.
That's all for today's ArXiv Computer Science Daily. If you found this helpful, please leave a comment, and subscribe for daily paper summaries. See you tomorrow. Thank you to ArXiv for use of its open access interoperability.